ठीक है सर, ठीक है. Okay. I
अरे
think
शुरू
Alpana
कर.
madam has also joined. Alpana madam. She is telling me that she has joined. Okay.
There are 7 people. नहीं, यहाँ तो दिखा नहीं कुछ.
She is telling me over this WhatsApp message कि मैंने join कर लिया.
मनोहरदीप सिंह है. आगे काफी लोग आ गए अब. 14 हो गया हम.
हाँ जी.
चलो आप.
हाँ जी, मैडम आ गए. ठीक है.
20 आ गए अब. हाँ.
ठीक है. Okay.
जी.
A very good morning to all of you. Professor Rohit Kumar Avasthi, Director, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. Dr. R.K. Sankaria, Head, Department of Electronics and Communication Engineering. My dear colleagues of my department and dear participants. I extend a warm welcome to all of you to this inaugural ceremony of this 1-week short-term course on research trends in integrated circuits and applications. I thank Professor Avasthi for sparing his valuable time and gracing the occasion. And it's a pleasure to welcome Professor Alpana Agarwal, Thapar Institute of Engineering and Technology, Patiala, who will be delivering expert talk in the inaugural session of this STC. Thank you, ma'am, for accepting our invitation. And I'm sure that the participants will be benefited immensely through your talk. Smartphones and deep learning technologies have disrupted the way we work and we design any system or we solve any problem. And all these have become possible with the advent of the integrated circuit technology. And in fact, all the electronic systems which we see and which we use in our day-to-day lives, no matter how big or small they are, from our mobile phones to our home appliances, our cars, even the space equipment, all these use integrated circuits. And in fact, the list of IC applications is endless and is continuously expanding. And during these 5 days course, we will be focusing on the recent trends and developments in the IC technology and the new materials and new device structures, which in fact triggered the growth of IC technology, will be covered during these 5 days course. And I would now like to request Dr. Ashish Raman, he's my fellow coordinator for this STC, to kindly elaborate about this short course. Dr. Ashish Raman, please.
Thank you, madam. Thanks for inviting me. Am I audible?
Yes,
Yes,
sir.
sir. Audible.
Yeah. So thanks, Mamta madam, for inviting me. So first of all, I would like to thanks our worldly director, sir, Professor Lalit Kumar Avasthi, sir, for providing this opportunity to organize this event. And without his support and the motivation, it would not be possible to have the such informative STCs on state of art topics. Actually, Avasthi sir always inspire us to a lot to organize such kind of the events. So thank you, sir. And I would also like to thanks our HOD, Dr. R.K. Sankaria sir, who has always supported us, giving his full support to organize such kind of events. Thanks, Sankaria sir. And further, I would also like to thanks our faculty of the department and all the participants. So, as Dr. Mamta Khosla madam has already talked about the development of the integrated circuit technology just now. So now I would like to add further that there are many recent explored materials as well as devices such as FinFET and then CNT FETs, then tunnel FETs and vertical T FETs, and after that many more that have triggered the growth IC device that is used in the IC technology. And our expert during this STC would talking about these latest trend in this STC. So now I would like to share with the participant that during these 5 days of the course, we have the experts from academia, from the premier institute of the India like NITs, then Thapar Institute of Technology, MIT University, and NITTR Chandigarh. And further, we have also expert from the industries like Coral Technology, which is a well-renowned industry in the VLSI tool domain. So they are just giving their talk in this STC. So they will learn the latest research trends, as well as they will get opportunity to learn about the latest tools and the target device such as FPGAs that are used for the prototype of the designs. So as we are having the expert from academia as well as from the industry, so by this way, this course will provide an interface between academia and the industry. Further, in view of the today's schedule, in the first session, we are having the expert from the Thapar Institute of Technology, Professor Alpna Agarwal, madam. Thank you, madam, for accepting our invitation. And in the second session, that will be covered by the Amandeep Singh, that is from the NIT Srinagar. So, with these words, now I wish all the best for the all participants, and I once again thanks to our director sir for sparing his time for this inaugural STC. So now I would like to invite our HOD, Dr. R.K. Sankaria sir, to share their views for this STC. Sankaria sir.
Thank you, Dr. Ashish. Good morning to all. Our Honorable Director, Professor Lalit Kumar Avasthi, the chief guest on this inaugural function. Professor Alpna Agarwal from Thapar University. Thank you, madam, for accepting our invitation. The other invited experts, heads and deans, the participants, we, the faculty and staff of Electronics and Communication Engineering Department, welcome you all on this 5-day short-term course on recent trends in integrated circuits and applications, which is being organized from 11th to 15th January 2021. We congratulate the coordinators of this course, Professor Mamta Khosla and Dr. Ashish Raman, for organizing this short-term course. As the objective of this course is to provide theoretical and practical knowledge of the recent trends in the domain of submicron MOS devices and their modeling for various applications. About the department, the Department of Electronics and Communication Engineering started its bachelor program in 1989. And later on, the MTech program also started in 2007, one in MTech EC and the other as MTech in VLSI design. And the PhD program is both in full-time and part-time is going on, which is being offered in various fields such as biomedical signal and image processing, VLSI design, emerging technologies, advanced communication engineering, autism, antenna system design, microwave engineering, RF circuit design, etc. The placement in the department have been excellent throughout, and even in the COVID times, in the last session, it has been more than 90%. As on date, the 27 batches of BTech, 13 batches of MTech has passed out. 32 doctoral theses have been completed by the department and 41 PhD theses are in progress at present. The alumni of the department is highly and supportively involved in the department's growth. Our Honorable Director, Professor Lalit Kumar Avasthi, has always been supporting us, encouraging us and motivating us to take up the innovative research works contributing towards national development. The department has been actively involved in organizing various workshops, short-term courses and conferences with more than 400 publications in reputed journals and conferences. Ever since its inception, the department is very much focused on realizing the innovative ideas and novel research conforming to Government of India's Atmanirbhar Bharat campaign. And now we invite our Honorable Director, Professor Lalit Kumar Avasthi, the chief guest on this inaugural function, to say words of wisdom. Sir.
Good morning and greetings from NIT Jalandhar. Professor Alpna Agarwal, Dr. Mamta Khosla, Dr. R.K. Sunkaria, Dr. Ashish Naman, Deans, Head of Department, faculty colleagues, and my dear friends. It has been nice to see this is the yet another course by Electronics Communication Engineering Department, the second today, and institute has completed more than 100 courses. This institute came in 1987 as Regional Engineering College Jalandhar, and later on it was rechristened as Institute of National Importance. Ever since its inception, the only focus is technological advancement, research, development, and contribution to society as well as for national growth. The institute has been doing very good, which is evident from the this year's NIRF ranking, where institute has surpassed in a single quantum 61 institutions. So, excellent work done by the faculty, and we have published more than 500 peer-reviewed publication in this current year. So again, excellent work of research scholars and the faculty members. And similarly, I think more than 110 such courses have been done by different departments during this pandemic time since January of this month. So excellent work done. The integrated circuit, as the topic is, and its application. So integrated circuit applications are everywhere, and starting from its inception, everyone wants a smaller and still smaller and still smaller mobile phone and a computer, and they want more capability, and more capability. So they want yesterday's computer, now today's mobile have much more capability than that. When we started working on computers, they were very big size and with very small memories of MB of memory, and you were finding it difficult. So now, with the latest advancements and into GBs of RAM and smaller miniature, it is integrated circuit which is working, and we are looking for more such miniaturization, and we look for how the capability and capacity of these circuits can be enhanced. So the trends which we can look into the global integrated circuit market was $412 billion in 2019, and it is expected to grow at a compound annual growth rate of 5.09% and to reach $502.94 billion by 2023. So this is where you'll find, and what on the other side, the latest technologies which you're looking for is nanotechnology, 3D integrated circuits, then universal memory, and you'll find in years multi-core everywhere. So, and networking, high performance computing, these are the things which are putting a lot of pressure on what kind of integrated circuits in the future we are going to have. So with these advances, I know the organizers, they have invited very galaxy of people from different places who will be deliberating on what are the latest trend in integrated circuits, and I hope everyone connected will be able to get input that how this market trend is going and how the technologies are advancing in this particular area, where we have reached and what is the benchmark and how we will be going further. And one more thing, that these short-term courses, definitely we should be organizing what the material which we are presenting here, the technologies which we are discussing here, they need to be brought into the books and they need to be given to the students as well. So we should be able to make our school students future ready. That should be the focus. With this word, I congratulate department, Dr. Mamta, Dr. Sunkaria for taking this initiative. Thank you. Jai Hind, Jai Bharat.
Thank you, sir.
Thank you.
Thank you very much, sir. Thank you very much, Avasti sir. Thank you, Head sir. I take this opportunity to read the brief biography of Professor Alpana and introduce her to the audience of this STC. It's a privilege to read her biography, in fact. Professor Alpana Agarwal is currently Professor and Head, Electronics Department, Thapar Institute of Engineering and Technology, and her areas of specialization are VLSI design and microelectronics. She has more than 27 years of academic experience and more than 29 years of research experience. She has served Siri Pilani at the level of Scientist B from 1988 to 1992, and then at the level of Scientist C from 92 to 96, and since 96 she is with Thapar Institute. She has handled approximately 10 R&D projects worth more than 4 crores from various government funding agencies, DOE, DIT, DST. She has worked on several projects at Siri Pilani, and she is also handling SMDP C2SD project of Government of India. She has, to her credit, many research publications in reputed journals and conferences. She has delivered more than 25 expert talks at various IITs, NITs, other institutes such as Kurukshetra University, BITS Pilani, Siri Pilani, and many more. She has organized approximately 15 courses and conferences. Her PhD thesis was chosen as one of the best international theses in the domain of VLSI by IEEE IS VLSI community, and she was invited to present her work in IS VLSI 2011. She was also awarded the best thesis supervisor in PI category under the aegis of SMDP VLSI Phase 2 project. And she has been handling various administrative responsibilities at Thapar. And she is also member of Board of Studies at various universities. And today her talk will be focused on advanced VLSI circuits. So now I invite Professor Alpana Agarwal to kindly deliver her talk. Professor Alpana, over to you, ma'am.
Thank you, Professor Mamta. I'm in fact glad. I'll first of all, I'd like to address Professor Lalit Kumar Avasthi, Professor Sankaria sir, Head of the Electronics and Communication Engineering Department. Thank you for considering me to be one of the speakers among the short-term courses. I will try to share some of my ideas, though I couldn't kind of collate a lot of slides and information, but I'll try to speak on something which is very close to my heart. Okay, let me, can I share my presentation?
Yes, ma'am, please.
Yes.
Why isn't right? Why it is not allowing me my PPT? Can you tell me, Mamta, how do I get it?
No, it's a neat link. There should not be any issue, like
Present now should give. It's not letting me, window is not visible. Share an application window, but I am not getting that window.
Oh, ma'am, you can do one thing. You can send your PPT to me and I'll share the screen from here. And this is what can be done right now.
Why it is not showing? Okay, I'll send it to you.
Okay, ma'am.
मैडम शेयर नहीं हो रहा क्या स्क्रीन जो है?
शेयर नहीं हो रहा.
प्रेजेंट नाउ से किया था मैडम इधर से?
Yeah, I'm opening present now, but it is not showing my window.
Okay.
Or the app which I want to share.
मैडम एक बार ना आप वो कीजिए इसमें क्या कहते हैं, एक बार लॉग आउट होइए, फिर एक बार फिर से लॉग इन कीजिए. मे बी सम नेटवर्क इश्यूज देयर.
Okay.
Meanwhile, ma'am, you also send your PPT to me. Log out हो गया. मैम आपका माइक ऑफ है.
I have sent you, but it's still not allowing me to share.
कुछ इश्यू आना नहीं चाहिए. मैम आप काइंडली आप मुझे भेज दीजिए अपना पीपीटी.
मैंने भेज दिया.
ओके, आई गॉट इट.
You may turn it on. It's not allowing me at all. Can you check the permissions? Why it's not allowing me?
अरे वो शॉर्ट कोर्स चल रहा है.
आशीष आप चेक कर लीजिए परमिशंस.
मैं वही
Are you able to open it?
चेक ही कर रहा हूँ मैं उसमें.
हाँ, open तो हो गया.
आ नहीं रहा. इसमें कोई रिक्वेस्ट ही नहीं, इसमें ऑप्शन तो कुछ आ नहीं रहा ऐसा.
मेरे को तो वो ओपन ही नहीं करने दे रहा. विजिबल ही नहीं हो रहा ऑप्शंस में.
Is it visible? My screen is visible.
Yes.
Is it open? I'm not able to open it. I'm it from my Explorer.
It's not
Not visible.
no, it is visible. It's visible. It's coming in. Let's ask the participants if every fine. So, sorry for the interruption and thank you for inviting me to a short-term course on recent trends, recent research trends in integrated circuits and applications. I'd like to briefly touch upon in some of the areas which are kind of important and the way the designs are shifting now. So first of all, I have been given a topic, advanced VLSI circuits. So what do we mean by advanced VLSI circuits? Next slide, please. So I take up the VLSI first. Is it very large scale integration? I think, Mamta, it is not in PPT mode. You have opened there.
This format is not, I cannot open it in my PC. That's why I'm showing, yeah.
Okay, no problem, no problem. So traditional VLSI definition used to be very large scale integration, but is it the only definition? No. I think from a student perspective, I believe there are plenty of students who have joined the STC. It's very large salary income. Why people go in for VLSI for now several decades? I think I had been into it for last 3 decades and I'm seeing the top VLSI designers or the talented VLSI designers are getting very handsome salaries. But it's not easy enough from a student point of view, it requires very laborious study indeed. And to my students, I always say it requires very long student involvement. So VLSI is not just about saying large scale integration or very large scale integration. Next, please. Now, this had been a old classic definition that when you go to something like 10 lakh devices or so, it is VLSI. Earlier definition used to be just 1,000 devices on a integrated circuit, which meant VLSI, but then definition changed and it is changing with time. In 2010, people said when you have 1 billion transistors on chip, we will call it GSI in the East, and West said we will call it ultra large scale integration. But they surpassed back and the numbers kept growing and new words could not be coined for the integration levels. We still call it VLSI. So maybe even today you have more than 200 billion transistors on a chip and still you call it a VLSI. Next, please. Now, when we move to the other two keywords in the topic, advanced VLSI circuits. So advanced and circuits. What do we call a advanced circuit? Does it mean a complex circuit, which means you increase the number of transistors and you increase their integration and complex integrations and all that, it becomes an advanced circuit? Or try to design a difficult circuit which is not easy to design is a advanced circuit and you apply newer techniques? Or is it a new application which you develop, you call it a advanced VLSI circuit I have made? Or when you migrate to a new technology, maybe as Professor Avasti was also saying, a 3D VLSI technology or a technology with a new interconnection which is optical or wireless connection on chip, or moving to nanotechnology scale, or that is advanced VLSI circuit. Or we talk about smart techniques or smart circuits which we make is advanced VLSI circuits. Or we incorporate some kind of learning within the chip, which is machine learning, deep learning, or some other kind of training algorithms within the chip, and we make it intelligent, which can decide many things of its own based on the experience. Isn't a advanced VLSI circuit? Or what? There are plenty of things which you can call to be a advanced VLSI circuit. Okay, next please. Now, these are some of the applications which I have put on a slide, but right from our hand, a mobile phone to any electronic gadget which we use today in our life has VLSI involved in it. Be it in our kitchen, we talk about a microwave oven, we talk about a refrigerator, or any other kind of a control, any kind of a machine which has an electronic display, or you talk about our televisions, or any other gadget you talk about, everywhere you need integrated circuits. And when you want an intelligent integrated circuit or a smart integrated circuit, it involves a lot of work which goes into it, and therefore it is, in my view, advanced VLSI circuit. The vehicle, any vehicle which you use today, a car, which has very nice features, involves a lot of integrated circuits, to rail or airway, aeroplanes or helicopters or whatever does it you talk about. In healthcare segment, we look for any kind of electronic gadget, be it a glucometer at our homes or a blood pressure BP measuring instrument, or be it a portable scanning machine or a portable hospital moving in the villages. Everywhere you need a very kind of sophisticated systems involving VLSI. And we need portable systems and we need power systems because portable systems need to consume the least battery possible, and therefore there are plenty of challenges. It only says some of the things cycle, you design only chip, that is not enough. You have to fabricate it, you have to dice it, you have to test it, integrate it into a board, and even that is not enough. You must build a system around it. Then only we are Atmanirbhar Bharat. Okay, so we should be looking at not just designing and fabricating an integrated circuit. We should look for the application and the system for which we are trying to do. Nevertheless, but design and fab are very important integral parts of any system design which we do today, which is a sophisticated system. Next, please. Now, this is the growth in various sectors, the way it has progressed over the years. This you can see, it is a latest trend slide. Recently, last year, I did pick it up. The first increase is the consumer electronics segment, which is increasing exponentially. Obviously, the requirement of mobiles and the gadgets which we use are tremendously increasing. Not only that, automotive market is also increasing in an exponential way, but it is behind the consumer electronics. Industrial electronics, and I have not specifically put healthcare because healthcare is also included in consumer to an extent, because many of the devices we want to have them portable devices and we want to use them at home. Next, please. Now, this slide will also tell you how the semiconductor industry has grown over the year, and this growth only leads us to make advanced or more complex or high-scale circuits, which eventually give you a system with advanced features. Next, please. Next slide, please. Mamta, can
There was a call from head, so okay.
no issues. Okay, so now the way we have increased in integrated circuits, it is started way back in 1965, when most of, I think, our young friends were not born. It was my birth year, and it was my birth month as well when this paper of Moore came, April 1965. And whatever predictions he made are true and are still working in the integrated circuit industry. He predicted that every something like 18 months, the number of components on the chip will double. He never said transistor or gate or what. He only mentioned components. And if you see, and he made a prediction based on only 4 circuits which were present at that time. These were 4 processors basically. And if you see even today, it holds true. Next slide, please. So there had been many more, the way complexity has increased. And now this is one of the kind of memory chip complexity, the way it has increased. When I was working on my PhD and even prior to that, we could never think of a memory stick or a pen drive which we use today. And I always had a problem, how do I carry my data? And even the hard disk which I could buy used to be very costly and could carry even 256 MB of memory or something like that. And the first pen drive I got was in something like 2007 and from Singapore, worth 4,000 rupees, and it carried only 256 MB of the memory. Today we talk about a kind of very easily available 64 GB memory stick is the common which we carry. Okay, and not very costly either. Why it has happened is VLSI or the advent of VLSI, the way it has progressed, the technology which has reduced, which has enabled us to design memory which consumes less space, and therefore you are able to build a large memory space on the same size of silicon. So these are the kind of miracles which have happened due to VLSI. Next, please. If we see the transistor counts, the way complexity has increased, we have in 2020, we have already surpassed 200 billion transistors. Though the prediction as per this was only 100 billion transistors to be made in 2020, but we have even more than double of it. 200 billion transistors I saw 2 years back. Recently, I couldn't find a figure, but 200 billion plus transistors are there on a single IC today. Today, we cannot think of doing an IC individually. We could do it 25 or 30 years back when I started my career in 88. I think it coincides almost 87, 88, coincides with the birth of NIT Jalandhar when I started my career. And that time, one or two persons could design an IC. But today, you cannot think of the kind of complexities we have. There are hundreds of people working and thousands of people who work on one IC to get it done within 6 months or 1 year time frame, and it still requires a day-night hard work by each one involved in the team. Next slide, please. Now, this growth we have taken, and I think you can move on to the next. It only says that the kind of growth it is happening, you are trying to double. Yes, please move to next. What you see is the decrease in size of the chip as well as the increase in number of devices on the chip. So it is multifold, that you are reducing the size of a transistor and therefore the circuit, and at the same time you are able to build and integrate more number of devices on the same chip. In fact, even the die size has increased. To begin with, 1 mm die was even a good kind of a size, and getting a defect-free 1 mm square silicon was also tough. Today, people make it 1 centimeter by 1 centimeter devices with a yield of 70% or something like that, which is tremendous development in technology. This is only due to technology development. No role of designers over here are getting so good ICs. I think next slide. Designers have a much more role to play. This is only saying operating frequency. You can move to next as well, Mamta. This is power. So operating frequency increasing, power increasing, operating frequency increasing with the advent of technology is welcome. But power increasing with every advent of technology, because you are packing up more transistors, more devices, more circuit, is not welcome, because it becomes too hot and it burns off. If the kind of powers which were predicted, if we had gone on the same technology and kept on building our circuits, it will generate a heat where you could make an omelette on an IC. So that kind of temperatures were way back. Today, it would have touched the energy of a rocket or something like that. But it is fortunate that advanced circuits or advanced low power VLSI circuits allow you to consume less power, and people have come out with variety of power techniques developed the sleep mode, they developed the multi-VT transistors so that you can put on your devices to low battery mode when you are not operating it. And you kind of even designed the logic to be worked in sub-threshold regions by reducing the supply voltages, by reducing everything. Every corner was screwed to kind of reduce the power, and we still have working ICs and with very less microwatt and even less powers. Next, please. This I have covered. Next, please. So power management had been a key problem. Now, yes, move on, next. Yes. This is very important kind of a slide, which I love a lot. The technology gave us a kind of a lot, but as designers, we are still unable to utilize what is available to us. Now, see this brown graph, the way the technology is providing us how many transistors you can build on a chip, okay, per chip you can build. So per chip, when I say, I take maybe 1 centimeter square area, and you can even build something like 300 million or billion transistors on that IC. But do I have so many applications, or do I have that many designs we can come up with which can be fabricated over there? No, not at all. If this gap between kind of a industry, which is fabrication house, and this green is a design house, it is also growing, but the growth is only 21%. Here the growth is 58%. So this gap is widening. Now this was visualized by Government of India way back in mid-90s, and therefore Government of India said we need to develop manpower into VLSI design, and by that we started the phase 1 VLSI design SMD VLSI program. It started in 98. And they thought of that that time semiconductor market was 0.5%. Indian share was 0.5%. So that time it was thought of in 5 years we will make it 10 times to 5%. And when the first phase ended, we were already 7%. So that was a great success. And then phase 2 came, and then this SMD PC2SD came. And with every program, emphasis on manpower development had been there. So this had been a good initiative from the Government of India. And today, as Professor Avasti said, we have a pretty decent market share, more than 20%. And it is likely to increase in coming years with the newer policies of the Government of India. So, but what is important is with time, the focus on design has also changed. For example, in mid kind of 90s to something like end of that century up to 2000, the focus was on building circuits. We should be capable of designing circuits, be it digital or analog. We should be able to design the circuits and get them fabricated. It should be a kind of a usable device. 10 years down the road, people started talking about not only one circuit is good enough, you integrate the full everything on IC, and you have to have expertise on a IC manufacturing, and you should be able to get a successful IC. But in 20s, last few years, now the emphasis is building system out of it. IC is also not enough. We should have a system with application, and that will truly make us Atmanirbhar, and we will have our own Indianized systems. Okay, so we need to bridge this gap somehow. I don't know. I don't have enough ideas. I'm sure young minds like you will think about how to bridge these gaps. Technology is offering you a lot, but how to utilize the technology and benefit the society using it. That is what is the challenge in circuit domain as well today. Next, please. Now, there are infinite challenges. I know I just saw there is a lecture coming up in coming days about challenges faced in VLSI. I'm just trying to mention, I'm not elaborating on it, but just mentioning some of them. There are two kind of issues or problems. One is microscopic and another one is macroscopic. Microscopic means I worry about what clock frequency I am going to use. Will my IC work on 10 gigahertz or something like that? Can I do it? Or what will be my power dissipation? Will it kind of have some kind of noise immunity, or what will be the level of crosstalk, or how I'm going to do clock distribution? Is my circuit reliable? Things like that. But macroscopic issues are more than that, but it has nothing to do with directly your circuit parameters, but above it. Time to market. Now, time to market is very, very important. Early, if you develop your product and launch your product in the market, then you earn the revenue. The late you launch your product in the market, already the money is lost. I'm sure you will know or you would have read the triangle rule. So the triangle, because every product has a lifetime which can be estimated like a triangle. The way the day it is launched, the uphill of the triangle starts, then there is a day of a peak for a product, and then it starts falling. And area of that triangle is your revenue generated. Now, if somebody launches a product late, so the triangle upslope starts late, peak will not change for that particular application, and at that peak, again fall will start, and there is a death. Everything which is born has to die, so there is a time when it will die. So the area covered in the second triangle, which will be very, very small as compared to the earlier triangle. The more later you launch your product, the least revenue you get. So time is money. So how do you kind of design it fast is also an issue. Okay. Another issue is now it is complex. It has millions and billions of gates. So you have multiple teams which are working on various segments. So how do you integrate between the teams? How do you manage those teams is an issue, because if you make many teams, integration becomes a problem. If you have less number of teams, then you take more time because teams have to do larger tasks. So how to do it? How to balance between the two, the number of teams and the time which you take. Another issue is high level of abstractions. Now what you want to do is, you never want to do from top to down everything. Maybe in the later slides, I would have mentioned the whole flow. But today, when you want to do more complex circuits and the number of transistors is huge, you can't design each transistor yourself. You have to use high level of abstraction, and you have to kind of rely on the tools and use them judiciously. You can also reuse your IPs which you generated for maybe some other application. So how to kind of tailor it and reuse it, and how to make it portable from one technology to another. Okay. And very important, predictability. What can you predict what is going to happen next and you can start doing it early. You can save time and hence you can make money. And these are not only the few things, there are many more of them. And I'm sure Ma'am Chandel will be covering it in her lecture. Okay, next please. Same is the problem as you go ahead and you have more difficult advanced circuits, evaluating those circuits is also difficult. Now, when you talk about even just a digital circuit, you have only what you are worrying about is a cost, testability, manufacturability, reliability. These are common, but you are talking about speed, power, energy, the maximum. These are the main issues. But when you go to analog, this is not the only issues. Speed, power, energy, everything is also required there, but their performance is measured more critically, and even a small noise or a small error can lead to failure of the circuits over there. And linearity and many other issues are also important. How the slews or the offsets and everything, a small thing may disturb it. Another important thing is the process variations in both, be it digital or analog, the performance varies a lot by your process variations. In analog, it becomes much more critical. So can you make process independent? To me, it is an advanced circuit you can design which is process independent. So can we do it? Yes, we can. Next slide, please. There are many more things. These are various abstractions, and every abstraction level is important, and you have to kind of work at all the levels if you want to do a good VLSI designer, or you want to do the best product out of your work. Next, please. This is typical design flow, ASIC design flow, which we use. All students would have done it. Front end and back end. We used to have simpler design flows when we started our journey, but today it has become more complex because you are handling more number of transistors or more number of gates or the complex problem which you are addressing. So every stage you need to kind of validate or test your kind of designs, and you have to keep iterating till you get the best design. Okay, so many, what you would like to do is only work in front end and back end, somebody does it for you and it's available straight away. But who is that which makes it available is some of us who do it, or some of you who will go into the back-end design will make libraries available to others, the front-end users. Okay, so for every product from here to here, every effort is required. The only question is who does what. So when we say I used only a synthesis method, I did a RTL design and I synthesized and I mapped on FPGA. Okay, somebody has already built all the libraries for me, okay, which are mapping on to the FPGA. There had been a team who has manufactured, designed and manufactured FPGAs for us, and we could use them. Okay, if you are using a standard cell library, even then somebody has done all the design libraries and provided you with those libraries which you make use in the front end and got your chip manufactured by the fab. Next slide, please. So the more is the complexity, more are the efforts required, even in design, even in test, even in manufacturing, testing, everywhere. This is one flow. So I have put in this slide only for the students. Like the exposure makes a difference. Don't think if I am expert of RTL, that is end of it. Please do go through all the domains and be good at everything. Now, these are at demand. CMOS circuit designers, memory, analog, and RF designers. Now, if you are good at it, that means you are good at CMOS design and SPICE. These are the two things you have to expertise yourself. And obviously the circuit techniques, and you can be hired by any company. If you want to be on back end, be good layout engineer, and therefore again you need to have a CMOS technology exposure. You should have an exposure of full custom design and make optimal layouts. There are plenty of patents even coming on layouts almost every day. So you can be a good designer and handsome packages would be available. Next slide, please. I'm not going into all the details of it, but as you go to complex systems, advanced circuits, you build in multiple technologies, devices, you make new devices into the technology. Now, this interface, which is very important in our design fab cycle, there are three important entities. One is the foundry, which fabricates the IC, a design team which designs the circuit. Hidden is obviously the device modeling, everything comes over here. And CAD tool vendor who provides us the software tools and integrates the process information from the foundry. We also pick up design rules, simulation models, parameters, layouts, and finally we get kind of integrated circuits. Now see, if you design new models, new devices, okay, fab house has to fabricate them. They should be fabricatable, and then they have to model so that CAD tool pro vendor can integrate them into the software tools which we use, and hence the circuit designers can utilize those devices and fabricate ICs. So I see a lot of devices coming up in technology, many FinFETs with low power, high speed, advanced features coming up. So if they are also modeled, all of them, the latest one, whichever you do, think about if they can be fabricated and can also be modeled so that circuit designers can use them and provide advanced circuits. Next slide, please. Something wrong with this slide. There had been a triangle, and this triangle I had drawn to say how the complexity increases. No problem. Stay over here. It was something like this, this kind of a triangle, and the top was only a peak, a mountain-like peak, which started with the device, then circuits, and making then sub-circuit modules like adders, multipliers, or op-amps, or even PLLs. And the bottom line was the systems which you make from those devices or subsystems. So ultimate, the breadth of topic increases as you move from device to systems. Now, system can have a biomedical application. It could be used in satellite. It could be used in a automotive. It could be used in a gadget. It could be used in a communication technology or a communication device, or it can be used for processing in a computer. So you need to know that domain knowledge as well when you are trying to make a system out of it. So only doing a device or a circuit or a submodule will not work today. You need to have a lot of breadth, okay, so that you can build systems out of it. Next slide, please. That is what I again repeat over here. There are typically two kinds of people which are available. Even when we sit in interview committee, you people are looking for this trait in you. One is there are highly specialist people who will know everything about a topic X, whatever they speak, or maybe they have done a research into that particular domain, they will have a lot of breadth in and out. Everything will be known, but this would be very narrow. It will be but very narrow. Then another kind of people who will know everything but surface knowledge. They will not have depth and they are not easily changeable or adaptable. Okay, so that both the way it is a problem. One has to be more versatile kind. You should have a breadth of knowledge and you should be ready to go into deep and change yourself as per the requirement. So one has to be versatile and adaptable as per the requirement. You should be able to change and take a challenge out of it. Next slide, please. So now I will come to, now since you have more complex circuits, you are going towards systems, and system is not purely digital, not purely analog, because digital has its own advantages over analog, and therefore you want to do every processing in digital. But unfortunately, our world is analog, and all the signals we get from our environment are analog in nature, and therefore analog circuits are also important. And you want to do all the processing in digital, you have to convert the analog signal to digital. But before conversion, one element is conversion, analog to digital and digital to analog signal conversion. But even prior to conversion, you will need a pre-filter or a noise filter or amplifiers which can suppress noise and take the signal, and they are complex kind of circuits. So you have some analog portions and you have some digital portions. So typically any system will be a mixed signal system on chip, which you will do if you are making a single chip or multiple chips. But system will definitely have analog portions, will have digital portions. Typically, it will be on, if you see area or the circuit portions, analog might be 20 to 25%, and digital would be something like 75 to 80%. Okay, but when you see what fails, typically analog fails. 75% chances of failure lies with analog, and digital fails only 25%. If you look at the design time, that 80% of work can be designed in 20% of time, and this 20% of analog takes 80% of your time in a design if you compute the total time taken for such a system to be designed on a chip. So where this design is a problem, analog regions are the problem. So can I do analog using digital? Can I replace analog thoroughly, totally by digital circuits? That is what is smart, and people now have started doing it, and there are, I believe, for last something like 6-7 years, people are making attempt and doing it. People have removed op-amps totally from converters. People have started even doing all analog components, and they have started doing a pure digital kind of designs. I'll show some of them. Next, please. Because again, this slide says your challenges are mentioned, not just power, speed, and are the problem. You also have problems related to precision, which is disturbed by your noise matching, linearity, etc. Next, please. So all these things, can they be eliminated when you talk to or when you move to a totally digital circuit? And that is what is the research interest of our group at this point in time. We have started working on replacing totally mixed circuits mixed signal circuits by digital circuits. So the first attempt in this domain was we started doing even op-amp, replaced op-amp comparators, and then we came up with one example which I'll be showing, which is in converters. We have done converters totally digital way, which you can even synthesize using the you can kind of have a RTL code, you can synthesize and you can build a converter. So I take now few examples to elaborate on it. See, one first example is a applied intelligence. This example, which is a safety cocoon, you have vehicles running on highway, okay, and what you want is a car which is driverless, okay, and it should keep running. It should sense if there is a hindrance. It should speed down or stop depending on what kind of hindrance it is. If there is a high traffic or traffic moving with a low speed because of congestion, my car should automatically adjust to the speed. What it requires is multiple things. One of them is the response time when it responds. It can sense through various sensors the signal. You can measure the distance through various sensors. But because it is a real-time application and it might lead to accident if we don't respond it immediately, you require a flash ADC in this kind of applications. Flash ADC, so we have done that flash ADC using totally digital way, and that contribution has come from two of the key members it is Dr. Anil Singh and Ms. Ashima, who did this as her PhD work. And we have now that chip available with us. Next slide, please. You can see this is one chip which is already there with us, 6-bit flash ADC. It has been done totally in a digital way. There is nothing analog inside. And testing is going on, and second version of it is also coming up very shortly from the fabrication house. And so this is what I call a smart application or a smart or a advanced circuit, VLSI circuit, which kind of solves many of your problems of analog circuit design. So these kind of things can also be extended to many other things. So we have started doing on, for example, PLL, phase lock loop, the necessity of every chip. You do need a clock generator on every chip. So if I can make a PLL which is totally digital, lot of problems are solved. Okay. Another thing is not just converting it to digital. You should be able to kind of build some intelligence into it. So now we are putting up machine learning algorithms on chip, which will be able to make these chips much more smarter and intelligent to take decisions. Next slide, please. This is just one setup which shows. Next slide, please. Which shows that how we are testing our kind of that flash ADC. Another example in healthcare. Now, if I can have this small IC which you see on finger, I can improve the quality of life of a human being. We have so many ailments within humanity. Okay, there are people who are suffering from diabetes, heart diseases, plenty vision. Can I provide a implanted hearing aid? I don't have a device which is seen outside. I implant within a ear. I put it within that, and it helps a person solve the problem. Can I put an eye? I saw recently one eye being coming up. So you have so many people who can't see today, so you can provide them artificial vision. Like diabetics, the severe diabetics have to inject morning, evening insulin. Can I put in a insulin dispenser inside the body, and the human being lives a kind of a comfortable, normal life without injecting every day. Even glucometer measurement, every time you have to prick your finger. Can I not measure glucose just by putting my finger somewhere, or which is non-destructive kind? I don't have to prick my fingers and all that. So all these things are some kind of, I believe, the requirement of the society. And if those kind of circuits and systems can be done, it would be a great service to the society. So in that direction also we have started. Next slide, please. You will see I have put in one example here. We are trying to make a wristband for the measurement of critical health parameters. Okay, so here we are trying to make a non-invasive glucometer. Another PhD student is working on the problem, and this is midway, so I am not telling you all the more details. But just the golden, our Ayurveda method, Vad, Pap, Pith and Kaph. If we can measure those parameters and we can kind of predict the health system, that is another project we are working on. So these are 2-3 things which are also being taken care of by a variety of PhD students. Next, please.
Sorry, this is not visible.
I had a small video, but I think you can skip. Next slide, please. This is another kind of an example. Now, I would like to see my city to be a smart city where everything is automated. And I get good facility. For example, I can use the electric vehicle, so I should have plenty of charging stations. I should have my mobile, which caters to every kind of app or through my mobile itself. Where is the charging station? Where is the parking lot? If my garbage is full, so it should be automatically, there should be a signal transformed from garbage bin to the corporation that collect the garbage from here. It is full. If there is an accident, there is a immediate signal to the ambulance and the hospital that there is an accident and services available, and a patient is taken care of immediately. And if there is a specially abled person wanting to cross the road, everyone should be signaled around, and so that the person can cross the road easily. Today, you see in our cities, if you are able, especially able, it is difficult to cross even the road without the help. So all these things get automated. Environment, agriculture, for example, there is dryness, humidity reduces, the agriculture land needs a water spray. So it should be automatically sensed, and there is a drone or whatever, he sprinkles the water over the field. If there is a lack of manure, that is sprayed, or if there is a kind of insects which attack, they should also be kind of visualized, and there should be a spray to control them, of that nature. If all that is done, that is what is advanced VLSI circuit to me. And all these systems will require ICs somewhere or the other, or the signal processing circuits in every kind of sensors, the circuits, and then build around, integrate them to make the systems. I think that is, next slide, please. So that is all I would like to kind of talk about. And I sincerely acknowledge the Ministry of Electronics and Information Technology, Government of India, through which I get support in doing all the things and which have enabled me to develop. Dr. Chandrasekhar is right now Professor Bits Pilani, but he was former director of C.D. Pilani, who had been my mentor throughout my journey. I started my career under his umbrella, and he is the one who taught me all the VLSI and helped me reach where I am. Professor Prakash Gopalan, he is the current director of Thapar, and I forgot to write the earlier directors, Professor M.P. Kapoor, who gave me entry into the Thapar, and Professor Prakash Gopalan. They had been kind of very encouraging people and constantly motivated me and kind of supported my ideas and the way I could work over here. Last but not least, the VLSI design team at TIET, who kind of visualizes my dreams. I only think and help them do, and they are the people who can ultimately realize what I want to do. And next slide with your questions. I'd like to take questions if there are any. Thank you for being patient listeners to my talk.
Thank you, ma'am. Do we have any questions from the participants?
Hello, ma'am. Good afternoon.
Yeah, good afternoon.
Ma'am, I wanted to ask that what are the challenges that we face in analog circuit design currently?
Analog circuit design, and not just currently, every time. The thing is, like in digital circuits, you are only kind of optimizing power and the speed. There are only two parameters. In analog circuits, there are more than 7, 8 parameters which you have to optimize simultaneously. So you have linearity, you have a kind of slew rates, power, speed. Then you have to have power range, output power range, offsets, many more parameters. And you try to improve one, 3 others get disturbed. So it becomes very, very difficult. Another problem is digital circuits have time-tested tools available to help you out in your designs. But for analog circuits, the only tool which you can use is a SPICE simulator. So circuit design level simulator only is available to you. You don't have synthesis tools available even today. Why analog designs is much more difficult and complex and time-taking.
Okay, ma'am. Thank you.
And it has to be worked at a transistor level only. You have to work on length, weight, everything.
Okay,
Any
ma'am.
other
Thank you.
questions from the participants? You can write your questions in the chat box if you have any questions.
Right now, I don't see any question even in.
I think we're falling short of time also because I promised it will be till 12. So thank you very much, ma'am. It was a very
Thank you so much.
at the same time very interesting talk also, and there were many special takeaways from this talk which will definitely be very beneficial for the audience of this course, specifically for the people who want to carry out their research. Madam clearly told that what are the key areas where the people can work through various examples also. And for the persons who want to get good placements with VLSI companies, he clearly told you that what are the tools or what are the skills that you need to master. And thank you very much, ma'am, once again.
Thank you. Thank you.
Okay.
All the best to all of you.
Thank you, ma'am.
I wish all the very success to your short-term course. And is it the same link if I want to join some other session?
The link will be the same throughout the STC.
Okay, so probably I'll come back in.
Most welcome. Most welcome. It's our pleasure. Yes.
Thank you.
Thank you, madam.
Thank you. Can I leave the meeting now?
Yes, ma'am.
Thank you. Thank you so much.
डॉक्टर आशीष
हाँ जी मैडम
फीडबैक लिंक यहाँ चैट बॉक्स में मांग रहे हैं स्टूडेंट्स, तो आप फीडबैक लिंक शेयर कर लीजिए.
It's not particular for the every session. We will provide you the participant. We will provide you the feedback link on due course of time.
Or the feedback link will be shared in the WhatsApp group also.
Yeah.
Right? So all of you can leave for this session. Next session we have at 12:15 or it might get late. आशीष बता दीजिए कब start करना है because
12:15 ही है मैडम टाइम
12:15 पे करना है.
या
Okay, so participants will meet at 12:15 again. To the same link you need to join. Hello. Do we have Dr. Amandeep?
Yes, ma'am. I'm here. Good afternoon, ma'am.
हाँ जी, sorry for the delay.
It's fine. Ma'am.
पार्टिसिपेंट्स भी कनेक्टेड है ना सभी? आई एम ऑडिबल?
Yes, ma'am. You are audible.
आपकी आवाज नहीं आ रही है अमनदीप ठीक से मुझे.
Yes, ma'am. You are audible.
आपकी आवाज अमनदीप क्लियर नहीं है मुझे.
Clear नहीं आ रही हूँ.
थोड़ी आपकी आवाज थोड़ी कम है.
Okay. Let me check.
Okay, participants, so sorry for the delay in this session. The speaker for this session is Dr. Amandeep Singh, and he did his PhD on the topic modeling and simulation of carbon nanotube FETs for ultra low power application. And currently he is working as assistant professor at NIT Srinagar. And he has many research publications in SCI journals and Scopus Index journals and conference papers also. And he has worked as assistant professor at Lovely Professional University also and at NIT Jalandhar for some time. His talk will be focused on the carbon nanotube field effect transistors, their modeling, and the circuit application of these devices. So I won't take much time and won't stand in between his talk and you people. So over to Dr. Amandeep now, please.
Okay. Thank you, ma'am. I would like to thank Dr. Mamta Khosla, HOD, Department of EC, NIT Jalandhar, and Dr. Ashish Raman, sir, for providing me the opportunity to deliver this talk in this short-term course. And ma'am has not told that I have done my PhD under her guidance at NIT Jalandhar. Let's start. Let me share my screen. Hello. Am I audible, ma'am?
Yes, sir.
Okay, fine. Thank you, Ravi. So, I hope my screen is visible. My presentation is visible to all.
Yes, sir.
Yes,
sir.
Visible नहीं है आपकी.
Hello.
It's visible, Amandeep.
Okay, fine, ma'am. So let me start. As ma'am already told that my topic will be carbon nanotube based FETs and its modeling and circuit simulation. So I will start from the basic that how we shifting towards the carbon nanotubes and its application as a MOSFET. Before starting that, we will start from the materials. Okay, so basically materials, then CNTs, its applications at CNT FETs, then further types of CNT FETs, then somewhat basic of modeling and its simulation part, slightly simulation what software that CNT FETs supports. Okay, and then lastly some circuit application, and then challenges in the CNT FETs, and lastly conclusion. So let's start that why we are shifting towards this novel materials. Okay. So everyone knows that in VLSI we are shrinking down the technology starting from the micrometer to nanometer. So in today's era we are approaching towards the 5 nanometer, 10 nanometer. At this scaling length, we are facing so much short channel effects. So we need to overcome these short channel effects. So designers are looking towards the solutions. So there are multiple solutions toward that because silicon-based MOSFET is widely uh, important due to its can say cost and various properties. So designers first think about the structural engineering, that what we can do in this silicon based MOSFET so that we can play with the structure to overcome these short channel effects. So the designers come with the various solution, that is multiple gate or gate all around, or in production we can say that a FinFET is in production, where FinFET is the kind of multiple gate based FET. Clear? So one is the solution to play with the structure, and second is we can think about the new transport mechanism, that is lead to the tunnel FET. In tunnel FET, the transport is due to the tunneling, basically band to band tunneling, rather than this thermionic emission transport. And the last solution is to replace that material, means silicon material, with some other novel materials. Although we use some other materials like 3,5 compound materials for some other application, but in order to rectify the short channel effects, we can shift towards the 2D materials. Okay, so in today's era, the lot of work is going on the 2D materials. So before that, let us have some overview on that. What is dimensionality here? Okay, if we talk about 2D material, what is meant by that? So first is the zero dimensional nanomaterial. So what do you mean by zero dimensional? So here dimensionality is the number of dimension which is responsible for the transport of the charge, or means by in which direction we can give a current. Okay, because current is basically transport of charge. In zero dimensional, there is a no dimension which is responsible for transport, means the atom is confined in a place, it is not allowed to move. So zero dimensional material in which there is no dimension responsible for transport, so basically it is an insulator. Then comes one dimensional nanomaterial. So electron, the charge carriers, can move in only in one dimension. Okay, so that is one dimensional. Then comes two dimensional nanomaterial, in which the electron can move into two dimensions, not in the third, and three dimensional in all the dimensions. So let us take example. If we take about a nanoparticle or a powder, nanomaterial based powder, so that is a zero dimensional nanomaterial. Okay, in which, because the here the dimension is in nano, so atoms are confined in this space, so they are not allowed to move the charge carriers. Okay, so this is the zero dimensional. We will deal with the one dimensional nanomaterial in this presentation, that is basically nanotube, and the nanowire can also be a one dimensional. Okay, so here the transport will be only in one dimensional. Okay, so if we look at this nanotube, the transport will be in only this surface. Okay, this surface, so only one dimension, not it can be moved in this direction, only in this x direction, let it be this x direction, so one dimension. Second is, then comes two dimensional nanomaterial, 2D material, which we always talk about, that graphene. Okay, so graphene is basically a 2D sheet. In this is one atom thick layer. Okay, so the electron cannot move in this up and down direction, it only moves in this x and y direction. So two dimensional transport is possible in this graphene nanofilaments. And lastly comes the three dimensional nanomaterial. It is a bulk material which we are using in MOSFET. Okay, so bulk powder or bulk MOSFET, in which the electron can go in any direction. Okay, so that is the three dimensional nanomaterial. So we will start with the nanotube. Okay, so nanotube is a cylindrical tube which is a hollow from inside and having the diameter in a range of nanometer, and the length up to micrometer, millimeter or centimeter. So it's up to us that for which application we are using this nanotube. Okay, if it is in MOSFET, then we can go for nanometer also. But how we can use this centimeter, that these nanotubes can also used for some sensing applications, or you can say interconnects. So in that we can use a much larger nanotubes. So how these nanotubes are formed? So the basic material which we use for these carbon nanotubes is graphene. Okay, so graphene is 2D layer, 2D sheet as shown in figure. So it is only one atom thick. Okay, so thickness is only one atom, and atoms are arranged in this hexagonal manner as shown. So, but why we don't use graphene? Although we use graphene in various applications, but the disadvantage of graphene is it is not having a band gap. So if we look at the EK diagram here, you will see that valence band is overlapping with the conduction band. So there is no band gap in graphene, so it is very difficult to turn off. Okay, so due to this, the graphene is not used in the digital application where we need to turn off the MOSFET. Okay, we can use it in analog applications because there is a no band gap. Now, next is nanoribble. So, what is nanoribble? It is a cut of graphene in a particular structure according to the parameter, that is chirality vector and the length. Okay, we are having a graphene sheet. From that graphene sheet, we have to cut some portion, and in which orientation, in which style we are cutting that sheet, so that is called nanoribble. Okay, so the chiral vector here can be defined as the sum of two integers, which can be given as n into a1 plus m into a2. And n and m are the integers called chiral numbers, and a1, a2 are the primitive lattice vectors of graphene. So this will be more clear in the next slide. So here I am defining that what is chirality vector. So in this, if you look at this sheet, this is a graphene sheet. So here there is a one atom at every edge of the hexagonal. Okay, so we have to cut this graphene sheet either in this horizontal direction, okay, or in this vertical direction, or we can cut in at an angle also. Okay, so here I am writing two vectors within bracket 0, 0. If I am starting from here, if I am moving in this side, so I am making this n. These two parameters are called n and m. N is increasing while m is 0, and m is increasing while I am shifting towards this vertical. So if I am shifting in both directions, means horizontal and vertical at an angle, so it is like 1, 1, 2, 2, 3, 3, 4, 4 like this. Okay, that is how this chirality is defined, means in which direction we are cutting. So if I am cutting in this horizontal, then it is called zigzag. If I am cutting at an angle, it is called armchair. And if I am cutting in vertical, so that is called chiral. There is one also type chiral, which is not mostly used. Okay, so based on these chiral vectors, so CNTs are categorized as chiral, armchair, and zigzag. So n, 0 is zigzag with only one vector. If you look at this, that m is always 0 in this direction, n is only increasing. So I'm writing n, 0 generalized in a zigzag. Okay. In this 7, 7, they both are non-zero, and in this also both will be non-zero, because in this we can't cut like this. We have to cut like this. So whenever we are shifting towards this, then both will be there. Okay. So n, m is chiral, and armchair consist of both chiral vectors. So why I'm discussing this? Okay. So this is the basically again representation. If this is the graphene sheet, how I am rolling. If I am rolling in this, it means this is the axis. Okay, this is the axis, and rolling toward this axis, so it will be zigzag. And this is the axis, means at this direction, at some inclined angle, I am rolling like this. So this will be armchair. And in this, if you compare first with second, I have shifted 90 degree. Okay, so again, this is, if this is rolled about this, so this will be a chiral. So based on your orientation, the CNT can be made. Okay, so next is single wall CNT and multi wall CNT. So CNT can be single wall or and also multi wall. So it's basically multi wall means if I am having more number of CNTs, means one over another, concentric. And while fabricating, we got these multi-wall CNT FETs more easily. Okay, so it is tough to fabricate single wall CNT. And these multi-wall CNT is basically used for the interconnects, because in this again the band diagram is hard to adjust. It is having small band gap. Okay, band gap. So multi-wall CNT again used for the interconnects because it is having some metallic nature. In this single wall, we can have two nature, either metallic or semiconductor, based on these chiral vectors. So why I am discussing these chiral vector? Because in CNT, we have to consider this band gap and its diameter. So this both diameter and band gap depend upon this chiral vector. So here are the formula. Diameter is under root phi by pi a under root n square plus m square plus 2nm, where n and m are chiral vectors. A is the interatomic distance between carbon atoms, okay, which is a physical property of carbon, which is not in our hands. And V pi pi is again carbon pi pi bond energy, which is again its material property. So here, if we exclude A and V pi P, we are left with this diameter, e.g. indirectly inversely proportional to diameter, and diameter directly proportional to this. So means both diameter and band gap depend upon this chiral vector. So how we are going to realize this CNT, or how we are going to cut the graphene, that will decide the nature of CNT. Okay, because this is the band gap, we need small band gap or higher band gap, that will depend upon the diameter. So this is having a, we are having a table, one table, which is explaining that if I am having a 3-2 chiral vector based CNT, then its diameter will be in nanometer 0.3 and its band gap will be very high. Okay, so as we are going towards the increased number of chiral vectors, so diameter will increase because it is directly proportional, but your band gap will decrease. Okay, so if we are going to increase up to this much, 5 nanometer diameter CNT, its band gap is very small. Okay, so it is very hard to turn off. So basically we used the band gap in the range of 1 electron volt, because for silicon 1.1 electron. So we use 1 electron volt, and because most of the time we use zigzag CNT, so we use that 11,0. Okay, n, 0, 11,0. In this we are having armchair and chiral CNT FET for the representation purpose. In this, if we look for this 7,3 having diameter 0.7 and EG as 1. Okay, or we can go for 1 nanometer diameter also, which is having around 0.85, 8 or 0.9, you can say band gap. Okay. So now CNT conducting properties, because we have to use it for MOSFET. So let's see that how CNT is going to behave as conducting. So as I already told that CNT can either be metallic or semiconducting. So how it is decided? Here in chiral vector we are having two vectors n and m. So if n minus m factor is divisible by 3, then CNT shows metallic nature. Okay. If n minus m factor is not divisible by 3, then CNT shows semiconductor nature. This is the deciding factor. So here I'm writing like 13,0 is most commonly CNT used for CNT FET with diameter 1 nanometer and band gap having 0.89 electron volt. Okay, so this is the deciding factor how we are going to cut CNT. So based on that, it is going to behave metallic or semiconductor. So this is the 77 CNT, okay, in which n minus m is 0. So it is metallic because there is no band gap. Here is 4,2. Okay, 4,2 is 4 minus 2 is 2, so which is not divisible by 3. We are having some band gap. Now here are synthesizing CNT.
Actually, we have to specifically concentrate which faculty, one or two faculty to be made in charge for that, and they have to continuously monitor, and we have to make the students, minimum certain students, we try to ask them to.
Is anyone asking question?
Before CPET, definitely the bright students will.
I am facing
As well as ask some of the bright students to write the online examinations of
Kindly switch off your microphones.
I just request someone has turn on his mic. Please turn off that mic.
Kindly switch off your microphones. Yeah, Avanti.
Okay. So next is the synthesizing CNT. So how to synthesize CNT? Okay. So CNTs can be synthesized by CVD and arc discharge method. There are two methods. So the problem in synthesizing CNTs, I'm not discussing that method because that is related with fabrication. So I'm going to discuss the problem, that what is the problem in synthesizing CNTs, that is controlled chirality and single wall CNTs. Because when we try to grow the CNTs, it grow in the form of bundles, or you can say multi-wall CNTs. And second is controlled chirality. What does it mean? That we require suppose 3,0, okay, 3,0 chirality. So it's not in our hand that if we can grow that 3,0. It can be 4,0, 2,0 because we are working at the atomistic level. So the controlled chirality is very much tough, and in which direction your atom will grow, that will be tough. Okay. So if I just look at that probability, so if probability of synthesizing CNT with all chirality possible, okay, so is equal to 1/3 of synthesized CNT will be metallic and 2/3 are semiconducting. Okay, because n minus m is divisible by 3. From that, if you look at the probability, so 66% of the CNT is fabricated or synthesized will be semiconducting. Okay, but there is a chance 33% that it will be not a semiconductor. So this is the problem in fabrication. Okay. So in CNT is formed in the form of bundle, that is multi-wall CNT. But still, researchers are able to fabricate CNT and result in the CNT FETs. So here are some reference example that CNT FET exhibit on current of 1500 microampere per micrometer as compared to 500 microampere per micrometer for silicon MOSFET at the overdrive voltage of 0.6. So it is having 3 times more on current as compared to silicon. And IBM has fabricated a full circuit based on CNT FETs, in which there are 10,000 CNT FETs are there. Although there are some issues are there for that circuit, due to that it is not in commercial use also, but still possibility is there. So here are some CNT key features, that its diameter we can use up to 1 to 30 nanometer, but we don't prefer higher nanometer diameter because its band gap will reduce. But we can use in this. Then length can be used less than 1 millimeter. Okay, but it can be used in centimeter also, but we generally use less than 1 millimeter. So it is semiconducting like silicon, and when it conducts, because when it is metallic, n minus m is divisible by 3, so it is having very high conductivity. Okay, 1000 times better conductor than copper. And it is either conducting or semiconducting depending on their structure. So let me tell you the reason that why it is very high current is there in this, because in this the conduction do not depend upon the mobility, because the transport here is ballistic transport. Okay. And in ballistic transport there is no scattering due to the collision of electrons. Moreover, the one-dimensional transport due to 1D transport in CNT, as we have looked at in CNT, the transport only take place on the surface of the nanotube. So only one-dimensional transport, the only 1D scattering is there. So there is possibility that very high on current will be there. Okay. And here are some advantage as electronic properties. So CNT as single material can give different band gaps with the variation of chiral vectors. If we look that silicon has fixed band gap, your 3,5 compounds fixed band gap. In order to vary the band gap, you have to shift to the other material. But here, by single material, we can incorporate the two different band gaps. And CNT offer ballistic transport due to high mean free path. In CNTs, the mean free path is in micrometer range, so it gives us the ballistic transport. So the mobility is very high. Okay. CNTs are compatible with high K dielectric. In silicon, we face the issues of dangling bonds when we do the fabrication with high K, but here it is very much compatible with high K. Less scattering due to 1D conduction. Okay. And the most important, the threshold voltage is independent of length of CNT and depend only on diameter. Okay. Now we will going toward the CNT FETs. Till now we have discussed that how CNTs are realized and what are the properties of CNTs, how it is going to behave semiconductor and metallic. So let us suppose we are going to use now semiconducting CNT in CNT FETs. So this is a basic structure of CNT FET. In this we are having substrate, over that we are placing CNTs. So here is CNT. This is the dope region under source contact, and this is again dope region under drain contact, gate, oxide. In this side we are having, if you look at this, we are having 3 CNTs. Okay, we can place n number of CNTs. So we generally model the current for one CNT, and then we can multiply the current within the number of CNT, because one CNT is responsible for some current. So we can directly multiply with the number of nanotubes used. But the thing is, we have to take care of this pitch. Pitch is the distance between the CNTs. Okay. If we place the CNT very much close to this, then there may be a capacitive coupling between the two CNTs. So we have to place accordingly. So now we will discuss about the types of CNT FETs. So basically we are having 3 types of CNT FETs. First is Schottky barrier CNT FET. Second is conventional CNT FET. Third is tunnel CNT FET. Okay. So what is Schottky barrier? So Schottky barrier CNT FET results when we use the CNT intrinsic, okay, purely intrinsic, because while we are synthesizing the CNTs, that is the intrinsic. It is a semiconducting nature similar to silicon, but silicon is doped. If we don't dope CNT, if we take CNT as it is, then it forms a Schottky barrier with source and drain metal contacts. Okay, so due to that, the Schottky barrier will form at contacts, and it is called Schottky barrier CNT FETs. So here, the disadvantage is that the ambipolarity will be there. Why? Because since it is not doped, so both charge carriers can be responsible for the conduction depending upon the gate voltage. If we give the positive gate voltage, electrons will be accumulated at the channel. Okay. If we give the negative gate voltage, so holes will be accumulated at the channel, and again current will be there. So the current will be always there for negative gate voltage and positive gate voltage. So it is not going to switch off properly. Okay, it is going to ambipolar characteristic instead of unipolar. So this is the disadvantage. So again, it can be used for analog applications, not for digital. And more is sub-threshold slope is always larger than the 60 millivolt per decade. So next is, can we use this CNT FET as a similar conventional MOSFET? Yes, if we can dope this source and drain CNT. Okay, we have a CNT, so we have to dope only on this source and drain side, then we can realize the conventional CNT FET. So this is the similar to the conventional CNT FET. Here conventional MOSFET. Here CNT FET is there, in which we are doping this N type on source and drain side. This is intrinsic. Okay. So in this, we can shift close to the 60 millivolt per decade subthreshold slope. And last is the tunnel CNT FET. Similar to the tunnel FET, we can realize the tunneling operation in CNT FET also if we can dope the source side as a P and drain side as a N. Okay. So it is similar to conventional tunnel FET, only we are using the CNT material instead of channel. So here again, the subthreshold slope will be smaller than 60 millivolt due to the band-to-band tunneling phenomenon. So here is how SPCNT FET work, that is Schottky barrier. So if you look at this this side, this is basically a conventional MOSFET, or you can say conventional CNT FET will also work like this when it is doped, because there is a smooth transition, because metal is you can say metal is full of energy charge carriers, and when we doped source and drain very much high, so there is no mismatch or very small mismatch of the Fermi level, so this smooth transition is there. But if you look at the Schottky barrier, this is intrinsic side and this is metal, so there is a Schottky barrier will formed at this junction. Okay, so in this barrier will reduce the on current. Okay, we have to overcome this barrier. This is in off condition. So if this is in on condition, we are applying VGS high. So this band is shifting, but still there is a Schottky barrier is there. So this Schottky barrier, because in order to get the current, this electron should overcome this barrier, either through tunneling, there is a tunneling is there, or this energy, overcome this energy. So this will reduce the on current also. Yeah. So here I am representing some comparison of the different devices possibilities with this CNT FETs. Okay. So here I have simulated it in nanoticad Vidus tool, which I will tell you further, which is the only available tool for CNT FET simulation of the CNT FETs. So here conventional Schottky barrier and tunnel FET are simulated for the subthreshold slope and on-off ratio. So if you look at this, in conventional, the on current is high, okay, and off current is intermediate in between tunnel and Schottky. Okay, in Schottky barrier, the on current will be low, but the off current is also high because it is hard to turn off. But in tunneling, due to its Venn diagram, because one is P side, second is N side, so there will be very less off current. And again, the problem in tunnel is less on current also there. So, but if you look at overall on to off ratio, tunnel FET is very much good. Okay, excellent. And again, subthreshold slope is much better. But we are focusing on this conventional FET. Okay. So here is the modeling. We will start with the modeling of CNT FETs. So here is standard MOSFET and here is CNT FET. If you look at these equations, IV current equations, here this is the familiar equation mu W by L C oxide Vg minus Vt into Vds. Okay, so here the current depend upon the mobility, spatial dependence, that how much wide your transistor is, W by L, charge in channel, okay, and then bias dependence. These are the factors. If you look at the CNT FET, this is the equation for CNT FET. Here, bias dependence factor is the carrier injection determined by the states between source drain Fermi levels. Because CNT FET is made from graphene, and graphene is 2D material, and in 2D material the density of states is very much low. Okay, so due to that there will be very small carrier in this CNT, and there will be charge injection from this metal contacts, because metal having full of charge carriers. So there will be injection of charge carrier from metal to CNT FET for the conduction. So this is the bias dependent, how much charge carriers are injected in this. Okay, and then come the transmissions at contact. This transmission is contact is basically related with the scattering, 1D scattering, when this electron will going to enter this contact. Okay, that scattering mechanism, and this charge in channel is basically calculated with density of states of the CNT. Okay, so this is the equation we generally use for the 2D materials or nanoscale MOSFETs. Okay. So here I am discussing about the compact modeling. Okay. So there are a lot of modeling methods, numerical, analytical, but the most important model we use as a compact model when we look for the circuit application, because it will give you the quick results in the circuit simulators. So mainly focused on digital application, okay, at the nanoscale gate lengths. And here the model is restricted to single tube. We model for single tube and then we multiply it with the number of tubes. If we going to fabricate with the 3-4 nanotubes, then just we can multiply it by 3 or 4, because one nanotube will carry that much current. Okay, so formulations focus mostly on describing the DC behavior. Okay, here because we are going for IV characteristics, so this is basically describing the DC behavior. If we have to describe the transient behavior also, then we have to include the CV characteristics also. Okay, so this is a flow chart of compact model. We will start with the diameter, because this is the starting point of the CNT, because CNT, when we form CNT, the only thing we can control is diameter. Based on that, we have to calculate its band gap and everything else. Okay. So from diameter, we go for this. The voltages VG, VD, VS, we define that subband minima, which is responsible for the conduction, and then control potential, the potential at the CNT source drain Fermi level. Okay, what is the Fermi level at source and drain? And this is the pre-computed parameter alpha and delta flat band. Okay, flat band is for threshold voltage variation, and alpha, I will tell you that what is that factor. Okay, so these are the specific voltages at source and drain side. Okay, psi s drain, which is the function of this control potential, subband minima, and the source drain Fermi level. So this is basically Boltzmann constant into temperature. So that will going to give you the current based on these voltages. Okay. The main quantities here is surface potential, VCNT, and the specific voltage that depend upon the surface potential, subband, and the source and Fermi level. The conduction band minima for the first subband is set to half of the nanotube band gap. I'm not going into calculation much, so it can be calculated with the 0.45 divided by the diameter. Whatever the diameter you are going to use, you can fill here and you can calculate the subband minima for that calculation. So here is the famous Leander equation is there, which we have discussed priorly. Okay. So here is ID is 4Q KT by H summation for the all subband minima, although we use only first subband minima, and log 1 plus exponential of psi s and psi d. So here we need to calculate basically psi s and psi d, because this is everything constant h, k, t, q. Okay, so psi I, where I is source and drain, is given by the potential at C and T, subband minima, plus mu. Mu is the source and drain Fermi level, divided by KT. Okay, so this is the equation for the simple CNT FET. So here, for Schottky barrier CNT FET, there are two cases are there. Either VGS is less than 0, then this will be the equation. For VGS greater than 0, this will be the equation. Okay, here phi effective, this is basically the effective Schottky barrier height, because this is your source drain Fermi level, that will be calculated by the Fermi level, Schottky barrier, because barrier is the function of your Fermi level at source and drain and Fermi level of your nanotube. Okay, so that is going to form the barrier. So now why I am discussing these two possibilities, because in Schottky barrier, either you can give positive gate voltage that is going to lead this, or you are going to negative voltage that is going to lead this. Both are responsible for the conduction. As I have already said, that when you are not going to dope CNT, the both gate voltage is going to give you the charge carrier for the conduction purpose. So these are the two possibility. Okay, when you are giving the positive voltage and negative voltage, for that there are the two cases. Okay, so these sign conventions also change these two things. Okay, calculation of the surface potential. Okay, VCNT depend directly on gate bias. More the gate bias, more will be the surface potential. The other factors is oxide capacitance and the charge on nanotube. Okay, so this is basically VCNT is VGS minus the charge on the oxide, the potential at oxide. Okay, this is potential at oxide, which is given by charge over C oxide, and charge is given by this expression. So if you look at this VCNT depends upon QNC, QCNT, and QCNT depends upon VCNT. So these two equations form the self-consistence equations. Okay, in order to solve VCNT, we need QCNT, and in order to solve QCNT, we need VCNT. So we have to solve this using self-consistent approach. So that is going to take very much time. Okay, so which is not good for the compatible compact model. So we shift to this equation, which is proposed by the Kaushik-Roy. Okay, giving some assumptions. So here VCNT is basically VGS or VGS less than the subband minima, first subband minima. If I am using a 1 nanometer, and you know that subband minima is 0.45 divided by 1, it will be 0.45. So VCNT will be follow VGS when VGS is less than 0.45, and after that it is going to follow this. So this is the alpha pre-computed factor which I am discussing in flowchart. Okay, alpha VGS subband minimum like this, where alpha is alpha naught plus alpha 1 VDS, this one. So this equation will give you quick result that is compatible for the circuit simulations. So here is the graph. If you look at this, VCNT will follow VGS till 0.45. After that, there will be variation. Okay. So if it is VGS minus VCNT, that will be 0 till 0.45. After that, you can find the values. Now, let me tell you, if you are going to work in this modeling part, that first we can model this equations in the MATLAB. Okay. So in the MATLAB, we can plot the IV characteristics. So it is just a defining MOSFET. But when you need to take that model into circuit simulator, then you need to define it in the model that is compatible with the simulator, SPICE simulator. Likewise in Cadence or HSPICE, if you look at the model files, there are some PTM model files in which all the parameters are defined. Okay, or lookup table based method in which you need not to write the equations, but you can fill your values at which current voltage, what is the value of current. And if you are going to model the equations, okay, then how you can write the equation. So this is the simple Verilog A model. You might know what is Verilog. So this is for the digital, writing digital code in Xilinx, and Verilog A is to write the analog part of the equation. Here the value can be anything. In that only the value can be 1, 0. Here the value can be anything. You can write the equations. So here this is the simplest example of a MOSFET in which the if VDS is less than VGS minus V threshold, okay, then the equation will be beta, okay, into 1 plus lambda VDS into VDS 2 VGS minus VT minus VDS. Okay, and if VGS minus V threshold is less than VDS, then your this equation will be followed. Okay, so module NFET drain gate source parameter real. This is the threshold voltage. Okay, which I have defined 0.2. You can take its anything value. Beta is basically nu C oxide W by L ratio or K lambda channel length modulation, which I have taken 0, and this is in out drain gate source and electrical drain gate source real ID. Real is the parameter which is we are going to calculate, and this parameter, these real parameter are the defined constant values. Okay, so based on this you can make your device in a Verilog A compact model, and then you can call that device in the circuit simulator. Okay, so if I look at that CNT, okay, here I am writing if V gate is less than EG by 2, okay, then psi is same as VGS. Here I am writing EG by 2. Why? Because your subband minima is basically same as EG. Okay. Here Ci is else. If it is greater than, then I am writing the equation in terms of alpha. Okay. This is alpha naught, alpha 1, this. Okay. And ID, what is ID? C into log of this. Where C is, I have defined already. I have not written here. That is 4Q KT by H. So this is the compact model. Now, either you can make the compact model or you can take these compact models from the website of the Stanford University. Okay, they have already developed the benchmark models for the CNT FETs. First is Schottky barrier, then Stanford CNT FET model. This is conventional, and then virtual source CN FET model. This is the latest one, which comprise of the gate all around structure. Okay, this can be downloaded from this website, and you can directly incorporate these models into circuit simulator using any SPICE simulator. So this is the Stanford CNT FET model, in which this is the structure. This is only they have used top gate structure. Okay. So this is the L channel pitch. Okay. There is a pitch, this structure, and these are the parameters which they have defined, because while you are going to download, you have to work in their conditions. Okay, because they have written that minimum channel length can be used here 10 nanometer. You can't go beyond that. Maximum you can use unlimited. Okay, so the channel width. Okay, minimum is 4 nanometer, maximum you can use. Number of CNTs, again, because there is option there, how many CNTs you are going to use. And you will find that if for one CNT the current is 3 microampere, for 2 it will be 6. It is just directly multiplied. Okay, so this is the Stanford CNT FET model, and there are a lot of circuits have simulated using this model file, and there are good publications in this circuit simulator in the transactions. Okay. So this is your virtual source CNT FET model, which is the latest one, in which this is gate all around. If you look at this CNT FETs, the gate is all around this one. Okay, so this is the virtual source CNT FET model structure, which you can download and study further, and these are the various parameter given here. Okay, so the spacing between CNT, physical gate, and this is the part that 1 or 2 or 3. So here you can use the gate all around, top gate with charge screening FET, or top gate without charge screening FET. Okay, so you can use top gate also, and but the new option is the cylindrical gate along all around this. Okay, so using this CNT FET model, a lot of circuits are not simulated yet. So modeling part I have discussed. Next, if someone is want to work in the simulation parts, then the only tool available is the Nano TCAT Vidus. Okay, which is open source. The advantage is it is open source, so you need not to spend a large amount on the TCAT simulators, other TCAT simulators. Okay, so it is open source. You can download, you can install it on that Linux-based operating system. It will not run on Windows. Okay, or you can access online in the Nano Hub. But the limitation on Nano Hub is you are not able to change much parameters because it is fixed. Okay, and you require internet connection for that. But if you can download and install, then you can make any structure and there will be no internet connection. Then CNT FET circuit simulation. So mostly done in h-SPICE using compact models. Verilog A models are used, developed or benchmark. You can develop or you can use benchmark model also. And second thing, you can also use for lookup table method. First thing is proposing some novel structure, and then you are going to model that structure. That's fine. You are writing the equation. Second is you are only going to simulate a novel structure. Okay, so you can simulate in the TCAT tool. You can extract the IV characteristics, store in the lookup table method, and then you can call it in your SPICE circuit simulator to simulate your circuit using your novel structure based on that novel device. Okay, so there are two methods. Either you can propose your model, you can use lookup table, or you can use benchmark model also. So here is first fabricated CNT FET. I am just giving some overview. Okay. So here is nanotube. This is source and drain electrode. This is the alignment of the CNT. Okay, platinum and silicon as a this is a back gate, and platinum as a contact. And this is a fabrication that on silicon you are going to put CNT and then contacts and then gate contact, gate dielectric and gate contact. Okay, so how you are going to fabricate CNT FET. I am just giving you some overview, but why I am giving you this, that theoretically or in this talk it seems very easy, but there is some challenges in fabrication. And in CNT FET the challenge is only in fabrication. Okay, so that is controlled chirality. I have already discussed that it is very tough to synthesize a CNT with some specific chirality. Second thing is alignment of nanotubes, because you can imagine that nanotube is very small in the form of nanometer diameter, which can't be seen by naked eye. So if you trying to put into transistors or you are going to grow that, the alignment problem is there. Because if you look at this, the alignment is like this one. Although we need sometime alignment in this direction or this, and one CNT can be aligned this, other can be like this or like this. Okay, so an alignment problem is there. And the lastly is doping of nanotube. Okay, so why doping I am telling you? Because I have discussed with you that CNT is just a roll up of graphene sheet. So graphene is one atom thick. And if you look at the doping, like ion implantation, we bombard with some doping atom. Let us, if it is phosphorus, we bombard it to the CNT, and what it will do, it will eject the carbon atom and phosphorus atom will take place of that. And while calculating the chirality, we count the number of atoms in a certain direction. Okay, so this is slide 53. If I'm just going back, I'm going to explain it. Look at this. Okay, this is the atoms. So suppose I'm bombarding the phosphorus atom and I'm using zigzag. Okay, I'm using zigzag, and phosphorus atom is going to replace this atom, then your chirality will disturb. Okay, if it is going to replace this atom, then it's fine. But if it is going to replace this atom or this atom, then your chirality will be disturbed. Means your property will be disturbed. It is only one atom thick here. So that is why the doping is again very much tough. Okay. If you are able to fabricate the you can say nanotube, then it's fine. But after that, doping is tough. So that's why we are shifting to the electrostatic doped CNT effect. This is the one of the possible solution. Okay, and for that there is a fabrication already done. Okay, and my PhD work was in this to form the compact model for this electrostatic doped CNT effect. I'm just going to discuss not much because I have already taken my 1 hour, and I will quickly go from this. So in this electrostatic doped CNT effect, what we do, we don't dope source and drain region. We put polarity gates at source and drain region, and we apply some bias here. So by the application of bias, we play with the bands of this. Okay, band of this, and we got the characteristics. Okay, so this is the characteristic. If I'm giving the polarity gate as 0.8 volt, then this is the characteristics, which is the n-type characteristics, and this is the characteristic if I'm giving the polarity gate as 0. Okay, so this is the p-type characteristics. Although we tend to turn off the transistor at 0 volt. For turning off the transistor at 0 volt for p-type, we need to give here the negative bias. If it is 0 bias, it is going to turn off here. Okay, that I am going to explain here. So if you look at this, this is the only important slide here. If you look at this, so this is the gate, means this is the region underlying the gate, main gate, and this is underlying the polarity gate. So here the polarity gate is high. If it is high, this band is shifting towards down. This main gate is low, so this is up. Okay, so if you look at this, this is basically equivalent to n-type. Okay, in this VPG is low. Okay, VPG is low, VG is high. So this is equivalent to p-type. In this, if both are high, this is already on. If this is low, this is again on, but the conduction is due to P. Here conduction will be N. So these two cases are the important cases. So this is fine, N-type. In this, VPG is low. Okay, VG is high. Since VG is high, if you look at this, if suppose VG is low and VPG is again low. If VPG is low means 0, VG is 0. So these both are at same. If it is both are same, it means at 0 potential, it is conducting. As we are increasing the VG, VG is increasing, this band is shifting toward down and it is going to turn off. It is going to turn off the transistor. Okay, so it is going to turn off here. But if you want to turn off transistor by the action of PG, then VG will be 0 but VPG will be minus. Then this will be achieved when VPG will be minus. Okay, then you will find this characteristics here. Okay, after that it will be off. So this is the unipolar characteristics in the non-doped CNT FET. Okay, although Schottky barrier will be formed because it is intrinsic. Okay, that's why I have shown here Schottky. This is Schottky barrier. Okay, so this is the model related to that, in which VCNT, subband minima, and the inclusion of the polarity gate. Because in channel there is a role of polarity gate. Okay, so that will be included along with the other parameters. So this was the results, means what I have simulated from the tool, proposed compact model, and there is some semi-analytical model. So I found very much close result with that, and then it is simulated in nanoticad videos. Okay, and in this this is the simulations result I found, and in this it is giving a steep subthreshold slope, means very close to 60.8. The limit means the limit is 60 millivolts, so it is very much close here, and it is giving one order low off current also, and the most important is dynamic reconfiguration, means symmetric p-type characteristics. If this is n-type, symmetric p-type, so same device can be used as n-type or p-type depending upon your potential. So you need not to fabricate the two different type of devices. Okay, so based on that I have simulated SRAM. So in this is p-type, this is n-type, and this is again n-type. Okay, 6T RAM. This is the excess transistors, and this is your cross-coupled inverter. So in these p-type, this is V polarity gate P, which is negative of 0.8, negative of 0.75, and here V polarity of N, which is positive of 0.75. Okay, by giving this, these CNT FET will act as n-type and p-type. Okay, so if you look at this, same device can act as p and n-type. There is no need of new device to fabricate, although we need some extra biasing. Okay. So lastly, I just want to give you some areas which can be explored in this field. So the device oriented is CNT is very much new field. There are a lot of novel structures due in this field. Okay, then modeling related, compact model of the novel structures. Okay, some has proposed some novel structure and simulated only, but the modeling part is untouched, and the no compact model is available for tunnel CNT FET. So we can go towards the tunnel CNT FET also. And in circuit behavior, if you just working in the circuit domain, so you need not to go for modeling. You can directly download the model files and directly incorporate that model files into SPICE simulator to simulate it for the various circuits. Okay, and let me give you one thing that I have discussed: 3 models: Schottky barrier model, Stanford model, and virtual source. The virtual source model is very much untouched for circuit application. So anyone can explore a lot of circuit based on that model. Okay, benchmark model is available. You can perform your circuit simulations. So these are some references. Thank you from my side. If anyone having some questions, so I can take.
Thank you, Amandeep, for providing that valuable talk. So,
Thank you, sir.
candidates, do you have any questions? Kindly ask the questions.
The participants are, I think, mostly from masters and doctoral.
Yeah. So, if you are having any questions, so kindly ask.
Sir, what is the application side of this carbon nanotube? Where exactly in the current the product development, where exactly it is getting used? Sir?
If you are just talking about CNT, then CNT are used for the sensing applications, because CNT, you will see that CNT is very much reactive to open environment, so it is basically used in sensing application. If you talk about this MOSFET application, it is under research only. It is fabricated, but still not production is there. Okay, but from CNT point of view, it is used as a sensor.
Okay, understood.
Anyone else? How do we dope CNT? Basically, we use this ion implantation method. Okay, simple methods. But the thing is, the how to means how to dope CNT. It's not a challenge, but how to get a semiconducting CNT after doping. That is the problem. The methods are same. Okay, either you can use by diffusion or ion implantation, but the problem is to obtain semiconducting CNT. That is the problem.
Do we have any other questions from any other participants? Okay. So thank you, Dr. Amandeep,
Thank you, ma'am.
and sorry for keeping you awaited for a long time
No, 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 it's
today
fine.
for today's session. So the schedule for rest of the sessions has been shared with the participants. It has been circulated through email as well as in the WhatsApp group also. And tomorrow morning we are having a session of this is Mr. Ankur Sangal. He is a senior application engineer in Corel Technologies, and he'll be talking about the latest FPGAs and their use and their applications, their architectures, right? And the session will start at 11 a.m. sharp. Right. So if you have any queries, you can write in the chat box. And I was going through the WhatsApp messages. The problem of feedback link has been sorted out, I guess now.
Yes, madam, it is sorted out.
Sorted out.
I think feedback link is also provided at the chat box. So all the participants are requested to fill the feedback link from the chat box only. Okay. We will not circulate it on the your WhatsApp group. Okay. So kindly fill your feedback link on your chat box only.
Okay, thank you, participants, and thank you, Amandeep, once again.
Thank you,
Would
ma'am.
like to see you again also for some delivering
Yeah.
some lectures. Thank
Yeah,
you.
sure, ma'am.
Okay, okay, thank you.
Thanks, Amandeep.
Thank you,
have
sir.
provided, you have given a very wonderful session, and you have provided the basic knowledge of the CNT FETs, and also provided the some software that are available
Yeah.
at the open-ended. So thanks once again for providing your valuable talk. Thank you.
Yeah. Sure, sir. Okay. Thank you, sir. Thank you all for
Thanks, participants.
listening.
Thanks, participants. Kindly fill your feedback form within 5 minutes. Okay.
Day-1.